Log on, tune in, find out. Another good idea from Cambridge.
Our meeting this afternoon is Ulrich Goertz, who's going to talk on moduli spaces of abelian varieties with Iwahori levels.
Okay, thanks for the opportunity to give a talk here. So, I want to consider these moduli spaces abelian varieties with Iwahori level structure. In positive characteristic. So let's fix a prime number p. And we have the finite field with p elements, and we also fix an algebraic closure of fp, and then we can consider the moduli space AG. Okay, I guess we also fix some G, at least one, of principally polarized abelian varieties. So just of principally polarized abelian varieties. So, I mean, this space classifies triples where A is an abelian variety, then we have this principal polarization, and then I will also, although most of the time I'm going to ignore it, but I will also fix some level structure away from P, just to make this an honest scheme. So this is a level structure away from P, and so I'm going to consider the space only sort of over Fp. I will ignore the characteristic zero point of view, although of course the study of these spaces, or one important aim of this study is to get your hands on arithmetic properties of these moduli spaces also over the rationals, say. And then the main object of this talk is a variant of this, where I will impose some level structure at P, namely of Iwahori type. So a G I Iwahori is to be the moduli space of these abelian varieties, but with Iwahori level structure at P. So what is this? It's the space of chains of abelian varieties. So we have a chain A0 to A1 up to AG. And so here we have some maps, alpha naught, maybe alpha 1, and so on. Then we again have principal polarizations on A0 and on AG, and some level structure away from P. And here these alphas are isogenies, so surjective group morphisms whose kernel is a finite flat group scheme of order P, rank P. Lambda naught and lambda G are principal polarizations of A naught and AG. And then there is a further condition, namely that the composition, if I go from A0 to AG along all these maps, and then I use lambda g to identify AG with its dual, and then I use all the duals of these isogenies to go back to A naught dual and use lambda naught to identify it with A naught. So then I get some some endomorphism of A naught, and this endomorphism is required to be just P, multiplication by P. You know? So this endomorphism is P times identity of A naught. Okay, so this gives us some space, and well, obviously we have a forgetful map from this Iwahori space to AG if we just map a datum like this to A naught and the principal polarization here. And I want to discuss some aspects of the geometry of this space. So there are some local and global questions about the geometry of these spaces. Maybe I will start with the simplest example, which is actually almost a classical example, so at least it's well known for a long time. If G is equal to 1, then we are talking just about elliptic curves. Yeah? And in this case, AG is a modular curve. So AG, this is some smooth curve. And in fact, in a sense, here we cannot say much more about it unless we really take this level structure away from P into account. But since I don't want to do this, I can just say, okay, it's some smooth curve, but here you see actually a dependence on this eta. And this Iwahori space also is easy to describe, but is actually geometrically a little bit more complicated. Namely, it's the union of two copies of this smooth curve, and these two curves, they intersect in finitely many points. So this is the geometric picture, and you see that although here of course it's still very manageable, it is more complicated than just the space AG. So we have several irreducible components, we have singularities, these irreducible components intersect, and if G grows, then the situation actually becomes much more complicated. Okay, so let me first talk about the local structure a little bit. So in the example, I would call the local structure sort of the knowledge of the singularities here, that in the singular points we have two smooth curves intersecting transversely, and we can ask what's going on in general. And I mean, I don't want to really go into the details here, but I want to sketch how to investigate this local structure. And the main tool is to consider the following map, which maps such a chain of abelian varieties. Okay, we also have this other data, but it's not so important at the moment. Maps it to the chain of the tangent spaces of these abelian varieties, or the Lie algebras if we want. We can take the tangent space in the neutral element of A naught so this is just a chain of g-dimensional vector spaces. And if we choose bases of these vector spaces, then we can express these maps by matrices. And this means that here we sort of go from the moduli space that we are interested in to some linear algebra object. And I mean, as I said, I don't really want to go into the details here, but you can put here some object. So actually, what you want to put here is some quotient stack. So you have what's usually called the local model. This is some scheme defined in terms of linear algebra, and then you divide out some group which sort of corresponds to the fact that if you really want to describe these maps by matrices, then you have to choose bases. And since we cannot do this, in order to get a well-defined map, we sort of have to take the quotient by the corresponding automorphism group to make up for this choice of bases. And then you can define a smooth morphism here. So the smoothness then follows from the theory of Grothendieck and Messing, which tells you that sort of the deformation behavior of an abelian variety or even of such a chain, roughly speaking, is controlled by what is going on the tangent spaces. So since this is a smooth morphism, you see that the singularities on both sides are the same, and this reduces you to studying singularities of some linear algebra object. And I will just write down sort of typical singularities that come up in this situation. So let me write this down. The singularities of a GI are equivalent, smoothly equivalent. So as singularities, it's just the same thing, so to say, are equivalent to the singularities of this linear algebra thing. And I mean, I'm not really saying what this means, but sort of typical things that occur here are given by the following scheme. So ZRN, this is a little more general, so to say, than the setting here, but still I think it gives a good idea of what is going on. So here R and N are integers, or positive integers actually, natural numbers, and you consider the following scheme of n tuples of R by R matrices. So you have here M1 up to Mn. So all these are matrices of size R times R. And then you impose some equations. And the equations are that the product of all these matrices and also all cyclic permutations of this product, so M2 up to Mn, M1, and all other cyclic permutations should just be equal to 0. Yeah, so in other words, you start out with an affine space in R squared times n variables, the entries of all these matrices, and then you write down all these equations. Yeah, so for each instance, so to say, you get R by R squared equations. So you really have a lot of equations. But on the other hand, you can write them down in a very elegant form. And these are, in a sense, typical singularities that arise in the world of these moduli spaces. And okay, so from this you can prove. Okay, actually, I guess I can use these two just as well, right? Okay, so you can deduce some properties. So on the one hand, if you study these local models, you can deduce properties of these moduli spaces. So, for instance, you can show that this scheme is reduced and all irreducible components are normal with rational singularities. And in fact, an interesting consequence of this theory of these local models is that you actually can derive the same result for this ZRN thing. Yeah? So here you can really use the story the other way around and prove something non-obvious about these matrix equations. So the same holds for ZRN. And so I don't want to go into how you do this, but it's quite clear from this definition that you cannot work directly with these equations. There are sort of so many indeterminates and so many equations that it's impossible to sort of investigate this directly and try to understand directly whether, for instance, these equations define a reduced scheme. And so to just mention sort of two key ingredients to this proposition, you embed this local model into some affine flag variety, and then you use the theory of Frobenius splitting. So this somehow is the good framework to view these local models. Okay, so this tells us something about the local structure. I mean, I wrote down some specific results, and we also, in a sense, know that whatever question we have about the local structure, we can study in terms of these linear algebra questions. Okay, so what about the global structure? So in order to understand the global structure, what one does is to study certain stratifications of this space. And maybe the most important one is the Newton stratification. So what's this? The Newton stratification is given as follows. So if I have an abelian variety, then I can associate to it its p-divisible group. So I sort of take all the p-torsion, union of all the p-torsion points. This is a p-divisible group. And then I can take the isogeny class of this p-divisible group. I sort of divide out by the equivalence relation given by being isogenous. So and in fact, the set of these isogeny classes is well understood. This is the same as the set of all Newton polygons. So this isogeny class just corresponds to the Newton polygon Yeah, so I mean this is some polygon which starts at 0, 0 and then it ends at 2g and height g and I mean the sort of the slopes of the lines which make up this polygon are between 0 and 1, and so one extreme possibility is to have g times slope 1 and then all slope 0, and the other extreme possibility is to have slope 1/2 everywhere, and then there are some possibilities in between, and of course if g is large then there actually are very many possibilities in between, but anyway, I mean this is a thing that one can understand combinatorially quite well. So each isogeny class corresponds to one Newton polygon, and we just say that the Newton stratum of some Newton polygon is made up by all points, all abelian varieties which have this isogeny class, the corresponding isogeny class, as the isogeny class of their p-divisible group. So if nu is a Newton polygon, then we get nu the corresponding Newton stratum consisting of all A such that the p-divisible group has isogeny class given by nu. So this is a locally closed subvariety of AG. So it's locally closed. We just equip this with the reduced scheme structure, and it's known that this is a stratification in the strict sense that the closure of a stratum is a union of strata. Union of strata. It's pure in the sense that the boundary of each stratum has codimension 1. So if the Newton polygon jumps, then it jumps in codimension 1. In fact, I mean here these closure relations, they are also well understood in terms of these Newton polygons. So a stratum lies in the closure of some other stratum if the Newton polygon lies below the Newton polygon of the open thing. So here this topmost possibility, this is the open Newton stratum, and down here with all slopes equal to 1/2 we have the closed Newton stratum. So this is how the closure relations go. I mean these are actually hard theorems, and they were proved by Oort and others. I mean this purity was proved by de Jong and Oort. So these names I guess should be mentioned here. And as I said, I mean this is there is nothing to prove. Basically you see from this picture with the Newton polygons that there's a unique closed Newton stratum, and this is exactly the supersingular locus. So coming back to examples with elliptic curves. I mean, for an elliptic curve, as you all know, that E is called supersingular if the p torsion topologically is just a single point. And in this picture, the supersingular points here are exactly the intersection points. And so here in AG, since right now we are still talking about AG, we have the images of these intersection points. So we have these finitely many points in AG. And in general, an abelian variety is supersingular if it's isogenous to a product of supersingular elliptic curves. So this is a direct definition of the supersingular locus. And the structure of the supersingular locus is actually, I mean, at least quite something is known about this. So maybe let's denote this by SG. Then it's known that, for instance, SG is equidimensional of dimension G square over 4. And then I take the Gauss bracket of this number. And this was also proved by Oort and Lee, and it also follows by the purity result. Okay, so this is the Newton stratification on AG, but now let's consider the Newton stratification in the Iwahori case. And here things actually become more complicated. So so first of all, this is actually not a stratification anymore in this strict sense. Yeah, so in general, the closure, first, I mean, maybe first I should sort of, to make this clear, I should say explicitly what I mean by this. So we define the Newton strata NUI in AGI by just taking the inverse image of NU in AG under the forgetful map. Yeah. But in fact, so we call that here in this Iwahori moduli space we have these chains of abelian varieties, and the isogeny type of the p-divisible group is independent of which abelian variety in this chain I take. So you could also say that I just look at the isogeny class of any of the p-divisible groups of these abelian varieties in this chain. So the isogeny class of AI p-divisible group, this is independent of I for such a chain in our moduli space. Okay, so I can define these strata. I again have locally closed subvarieties, but okay, I had already said this. Let's write it down. This is not a stratification in the sense that the closure of NUI in general is not a union of other sets of this form of NU prime i's. but nevertheless, these loci, these strata are an interesting object of study, and they are sort of important for the understanding of this whole space. And I mean, maybe I should have said this before, but let me emphasize that understanding these moduli spaces with some level structure imposed at P, yeah, so as I do here by posing this Iwahori level structure, is in fact important in order to really get your hands on arithmetic properties of these moduli spaces, and in order to, for instance, use them in the Langlands program. Yeah, so in the Langlands program, you want to say that on these moduli spaces of abelian varieties, or on their cohomology maybe, you have an action of some Galois group of a number field, and also an action of the underlying algebraic group by Hecke correspondences. And in order to really have these Hecke correspondences, you need to allow level structure and also a level structure at P. Yeah, so this means that it's really important to understand these spaces as well. And so let's see what we can say in this case. Okay, we see that these Newton strata are not so well behaved, but nevertheless we can try to understand them, and I want to put some focus on the closed Newton stratum in the Iwahori case. So there is again, I mean, this is clear that there again is a unique closed Newton stratum. In AGI, namely, this is again the supersingular locus. Say SGI, and
so you had a chain, right? Of
yes.
abelian varieties. They were all isogenous.
Yes.
So this group, this isogeny class, is the same for all of them.
Yes. Yes. Right.
So you can. Why is it not a stratification? I mean, you can just look at the first one, right? So just the first abelian variety, principally polarized.
Yes.
And there, as you explained, that's a stratification. So why is it not a stratification?
Okay, why is it not a stratification?
Why wouldn't this property obviously be true, that the closure of strata, of a stratum is strata? Because that only depends on one abelian variety.
Yeah, but the point somehow is that these sets, they are not irreducible, and in some and neither are they equidimensional, and sort of in some strata, some irreducible components you sort of can degenerate, but in others you cannot. I mean, okay, I guess this is not a very good
maybe it depends how you define
explanation.
Stratum, but you have this forgetful map to the modular of principal polarized abelian variety.
Yes.
You're just looking at a pullback of a stratification.
Yes.
Yes, map. So pullback of a closed set is a closed set. So your strata, maybe they are not equidimensional.
Yes, I mean, okay, it's a closed set, but it may not be the closure of this thing anymore. I mean, it's not a formal consequence. So, I mean, okay, it's true. You have this this thing. So, okay, maybe let's see whether we can understand this here. So, we have that the closure is actually the union of some things like this. But now, if you take the inverse image, then it's true that the inverse image of a closed map is again closed, but it does not necessarily preserve sort of this relation. It doesn't have to be the closure again.
And it would preserve it if your forget format were finite. But your forget
Yeah,
format
okay,
is not finite,
yes,
is that right?
yes, it's not finite. Yeah. No, I mean, actually this map is, in a sense, it's very badly behaved. So from this point of view, the example where g is 1 is actually misleading. So for g equals 1, it's still, I mean, even there, it's slightly complicated in the sense that for one of these two copies, you have just the identity, and for the other copy, you have a finite map. You have a Frobenius-like map. So even there, it's sort of, you could say that it's slightly more complicated than it looks, but of course, in this case, it's still finite. And in the general case, about all you sort of can say as a general property is that the map is proper and surjective. But it's not flat, it's not finite, and it's actually very hard to understand the fibers.
Your unique closed stratum is not connected.
Pardon?
The closed stratum is not necessarily connected, right?
Right, it's not connected, yeah. I mean, even here you see this, yeah. The super singular locus is actually disconnected here. So, I mean, here you have these finitely many points, and so above here, these super singular points are exactly the intersection points. So this is not connected, and in fact, you see that. So in this case, I mean, for g equal to 1, you just have 2 Newton strata. You only have these 2 extreme possibilities. There is sort of too little space to put any polygon which is allowed as a Newton polygon in between. But you see that sort of here the open Newton stratum is connected, of course, but in the Iwahori case, even the open Newton stratum is not connected. So in general, they will have several irreducible components. Okay. Okay, so another thing we can say is that, so this is another bad property, so to say, but let me list it here. If G is at least 2, the super singular locus in the Iwahori case is not equidimensional. And its dimension is not known in general. I will come back to this later. We have some results in this direction, but not yet a complete result. So we call that in the case of AG, this was known. Okay, so okay, let me first use this thing. So in order to study this super singular locus and also in general the structure of these spaces, it's useful to compare the Newton stratification with the difference stratification. This is called the Kottwitz-Rappaport stratification. And this is at least roughly defined as follows. So recall that we had this description of the local structure, which came by the smooth morphism to some linear algebra object, roughly speaking. And this linear algebra object, this has a natural stratification I mean, very roughly speaking, this is a stratification by singularities. Yeah, so in the sense that the singularities of this whole space are constant along the strata. Yeah, the open strata are smooth pieces of this space, and then sort of if you go to smaller and smaller strata, then the singularities get worse and worse. So you can write this as a union of locally closed strata, and in fact in the sense of this pointer towards the affine flag variety, you can see the stratification by saying that once you embed this local model into the affine flag variety, it is a union of Schubert cells in this affine flag variety. And this gives you a stratification here, and this stratification induces stratification of the quotient, and then by pullback we get that AG is the disjoint union of certain locally closed strata, KR strata. And this is a finite union with some index set, which is usually called the admissible set. So this index set can be understood in terms of group theory, in terms of the affine root datum of the underlying group. Okay, so So let me tell you some things one can say about these KR strata. And this is joint work with Chiafu Yu from Academia Sinica. So all these KR strata AX are quasi-affine. Okay, R stratum AX is connected if and only if AX is not contained in the supersingular locus. And I mean, this again is a point where the level structure away from P plays some role. Yeah, so we certainly want to choose it in a way such that the whole space here is connected. So I mean, depending on what you do away from P, you can sort of arrange things so that the whole moduli space is just the disjoint union of several copies of the same thing. And then of course you have to sort of modify the statement a little bit. But for suitable level structure away from P, you can say that a stratum is connected if and only if it's not contained in the supersingular locus. And furthermore, if it's contained in the supersingular locus, is contained in the supersingular locus, then we can explicitly describe the variety structure. So then AX is the disjoint union of copies of a delinealistic variety for the group. Okay, maybe leave this call. Yeah, I don't know. Okay, GI, yeah, that's right, GI, and this holds for some suitable I depending on X. So here I lies between 0 and G, and this depends on X. And what's this group then? So for each x such that the corresponding stratum has this property, we find some index I and define the group Gi as follows. So this is the group over the finite field Fp, and it's given by its Dynkin diagram. Which we obtain as follows. So we take the affine Dynkin diagram of type C G tilde. Yeah, so the Dynkin diagram of type CG is just this thing, and the affine version, so to say, means that you have to add one vertex in this way, and then you can number the vertices by 0 to G. And now you omit the two vertices corresponding to I and G minus I. Yeah, so for instance, if I is equal to 1, then you would omit these two vertices. Yeah, so omit vertices I and G minus I from this affine Dynkin diagram CG tilde. So this gives you some disconnected Dynkin diagram. So Gi, at least over Fp bar, is just the product of 2 or 3 groups. And there's one more point you have to take care of, namely this group is not split, but the Frobenius sort of acts on the Dynkin diagram. So the Frobenius acts on the Dynkin diagram by the automorphism of order 2, by just flipping this, J goes to G minus J. Yeah, so in other words, this group is split over Fp squared and given by this Dynkin diagram, and then you just take the form over Fp given or corresponding to this Frobenius action. And then these delinear-Lustig varieties, they are certain subvarieties of the corresponding flag variety. Yeah, so delinear-Lustig varieties they are varieties of the following form. You take all G in this flag variety, so the quotient by Sambuel subgroup defined over Fp, and then you have a condition like this: G inverse times Frobenius of G is required to be in some fixed B double coset. Yeah, this is the definition of delinear-Lustig varieties. And so this W of course will depend on X, and in fact this dependence is in a very simple way once you know what this admissible set is. I don't want to write all this down, but since there is nothing complicated here in this translation procedure, how you get this delinear-Lustig variety. Yeah, so you have this explicit description of these KR strata, and in fact you can say more, namely the closure relation between such KR strata. This corresponds exactly to the closure relations of these delinear-Lustig varieties. You can, so as long as you restrict to KR strata which are contained in the supersingular locus, you have very explicit descriptions. And from this you get some corollaries. So let me write this down. What can we say now about the supersingular locus? So when you write down, so I mean there are certain choices of KR strata where it's very easy to see that they are contained in the supersingular locus, and this will give you a lower bound on the dimension of the supersingular locus. And using this you can say the following. So first is, if G is even, then the situation is relatively simple. Then we can say the dimension of the supersingular locus in the Iwahori case is G squared over 2. So one thing we see immediately is that the dimension of the supersingular locus is much larger than in the case of AG. And furthermore, we can say that every top dimensional irreducible component of SGI is isomorphic to the flag variety of the group. I take the symplectic group of rank G over 2, yeah, so SP2 G over 2 cross itself. And this isomorphism, we have this at least over K, over the algebraic closure of FP. Yeah, so here we know the dimension and we have a good understanding of the geometry of the top dimensional irreducible components, but as this sort of implicitly says, the supersingular locus is practically never equidimensional. Yeah? So there is some something left over that we cannot easily control. And what if G is odd? Then we actually only get some lower and upper bounds, so then we know that, so where does it go again? Then G times G minus 1 over 2 is less equal than dimension of SGI and is less or equal to G plus 1, G minus 1 over 2. And the supersingular locus has got irreducible components which are isomorphic to the flag variety of SLG and so these irreducible components that we understand here, so to say geometrically, they have the dimension of this flag variety, dimension G times G minus 1 over 2. Yeah, so this is this lower bound, and okay, I mean I should say all these corollaries. This is also joint work with you. Yeah, this is the theorem, and sort of the theorem is the main ingredient, of course, here. And we conjecture that if G is odd, then the dimension of the supersingular locus should be given by this lower bound. And I checked this for G less or equal to 5. So in fact, one can translate this into a combinatorial problem, the question of this dimension, but okay, as you can guess from this bound, so to say, the combinatorics is quite hard. And even for G equal 5, you have to use a computer program, and okay, I mean, I guess probably my programs can be improved a little bit, but it's in any case, it's not easy to check this for G significantly large. Okay, I think I will stop here. Thank you.
Questions?
Is there a lower bound for G even?
Now for G even we have, you mean a lower bound of the dimension of irreducible components.
Even for G odd, that's not a lower bound for dimension of components.
No, it's not, no, right. So I mean it's, whenever I write dimension, this is sort of in a very naive sense. It's just the dimension of the whole thing. I don't make a statement about irreducible components. And in the even case, okay, we have this equality for the dimension of the whole space. And no, I don't think that there is a simply available lower bound for components in the even case. So the problem is sort of that I mean at least not with these methods. They are somehow here we are comparing these two stratifications, and we get some good results in the case where sort of they fit together in a good way, but it's clear that in general they are not compatible. I mean, these stratifications are not refinements of each other, so there will be some sort of non-trivial intersections of strata, and with these methods we cannot control them. So I mean, as I said, there are methods to compute the dimension of the supersingular locus in a different way, and so in principle it's an algorithmically approachable question to compute this lower bound, or even the sort of the dimensions of all irreducible components in some specific case, but the combinatorics is so complicated that I'm at the moment not very hopeful that one could write down a general bound easily.
Any more questions? Okay, well, just before we thank the speaker again, can I ask who is interested in going out for a meal this evening?